Hey guys, my name's Salah Al-Sharif, and I'll be doing the Module 1 for the Chemistry Culminating tutorial this semester. So here's my presentation, and I'll be talking about theoretical and percent yield. So here's a funny meme if you guys would like to read that. And so yeah, let's get started. So chemical reactions in our real world don't always go as planned on paper, right? So in the course of an experiment, many things will contribute to the formation of less product essentially than what would be predicted. So besides spills and other experimental errors, there are usually losses due to incomplete reactions and other things like undesirable side reactions. So essentially, chemists need a measurement that indicates how successful a reaction has been. And this measurement is called percent yield. So to compute the percent yield, it's really important to determine how much of the product should be formed based on the stoichiometry of the chemical reaction. And this is called the theoretical yield over here. So the maximum amount of product that could be formed from the given amount of reactants. And the actual yield is the amount of product that is actually formed when the reaction is carried out in the laboratory. And then the percent yield is the ratio of these two. So it essentially is a ratio of the actual yield and the theoretical yield expressed as a percentage. And I'm sure you guys are already familiar with this. So here's the percent yield equation or expression. It shows the ratio between actual yield and theoretical yield times 100. So percent yield is very important in the manufacture of products. Much time and money is spent improving the percent yield for chemical production, like pharmaceutical production, for example. When complex chemicals are synthesized by many different reactions, one step with a low percent yield can quickly cause a large waste of reactants and expenses as well. So typically percent yields are understandably less than 100% because because of the reasons indicated earlier. However, percent yields greater than 100 are possible if the measured product of the reaction contains impurities that cause its mass to be greater than it actually is. Hey guys, so here is our percent yield practice problem, and it states in a certain experiment, 40 grams of potassium chlorate is heated until it completely decomposes. What is the theoretical yield of oxygen gas? The experiment is performed and the O2 gas is collected, and its mass is found to be 14.9 grams. What is the percent yield of the reaction? So essentially here we have the chemical equation for this reaction, and it basically demonstrates that potassium chlorate decomposes upon slight heating in the presence of a catalyst, obviously, but we don't really include that in this equation. Okay, so we first have to start off by balancing the equation, which is, so we need a 2 over here, and a 2 over here, and a 3 over here to balance out all the elements. So, and now first we have to calculate the theoretical yield of oxygen based on our stoichiometry. So let's list all the things we know. So the known, we have the given mass of potassium chlorate, which is 40 grams. We have the molar mass of potassium chlorate, which is 122.55 grams per mole. And we have the molar mass of oxygen as well, which is 32.00 grams per mole. And remember, it's two oxygen elements, oxygen atoms, and not simply one. So now we have to calculate the theoretical yield of oxygen and apply stoichiometry to convert from the mass of the reactant to the mass of the product. So essentially we have to find the moles of the reactant by using this equation. So moles equal mass over molar mass. So essentially for the potassium chlorate, our mass is given, which is 40.0, and our molar mass is 122.55 grams per mole. And then it turns out after you calculate this, the grams cancel out and you end up with 0.326 moles of potassium chlorate in the reactant side. And then now we have to use our mole ratio between potassium chlorate and oxygen, which is 2 to 3. So 2 refers to the potassium chlorate, 3 refers to the oxygen, and now we use the moles we have for potassium chlorate and put it into this ratio. So we have 0.326 over our unknown moles of oxygen. So then now you just cross multiply and you end up with 0.490 moles of oxygen. And now essentially we use these moles to find the mass of oxygen. So now we'd have to use this equation. So mass equals moles over molar mass, which then refers to the 0.490 moles of oxygen over the molar mass, which is 32 over here, so 32.00 grams per mole. And then calculated, the moles cancel out, and you end up with 15.7 grams of O2. So essentially this number here is our theoretical yield after completing the mole ratio between the reactants and the product we're trying to find the yield for. So now let's think about our result over here. So the mass of oxygen gas obviously has to be less than the initial 40 grams of the potassium chlorate that was decomposed. So now we'll use the actual yield and the theoretical yield. So actual yield, which is 14.9, and the theoretical yield, 15.7, to calculate the overall percent yield and basically assess how successful this decomposition is. Okay, so let me just erase this stuff. Okay, so our knowns are obviously actual yield, which is 14.9 grams of O2. So this was the yield found in the laboratory setting or in the experiment. And theoretical is basically 15.7 grams. And this is basically what happens if the chemical equation or the decomposition had no flaws. So and then percent yield, as we know, the equation is actual yield over theoretical yield times 100 to compensate for that percent. So our actual yield is 14.9 grams over 15.7 theoretical times 100, giving us an overall percentage yield of 94.9%. So since the actual yield is slightly less than the theoretical yield, the percent yield is under 100. And this is what usually happens in most circumstances or in most chemical reactions. So yeah, thank you guys. Okay, so after we were done that example, now we have to talk about the limiting reagent. And the limiting reagent in a chemical reaction is basically a reactant that is totally consumed when the chemical reaction is completed. So the amount of product formed is essentially limited by this reagent, if you guys know what I mean, since the reaction cannot continue without it. So if one or more reagents are present in excess of the quantities required to react with the limiting reagent, they're described as excess reactants, essentially. So the limiting reagent must be identified in order to calculate the percent yield of a reaction, since the theoretical yield is defined as the amount of product obtained when the limiting reagent reacts completely. So yeah, that is basically the premise of a limiting reagent, and it's important to maintain contribute a balance between the limiting reagent and the percent yield when it comes to different applications. Hey guys, so here's our second example for the tutorial, and it's the limiting reagent example, and it reads, given the following reaction, MgOH2 plus 2HCl reacts to form MgCl2 plus 2H2O. So it asks, how many grams of MgCl2 will be produced from 12 grams of magnesium hydroxide and 42 grams of HCl? So for this reaction, unlike the other one with potassium chloride decomposition, it has two reactants. So we really have to figure out which one of these reactants is going to be the limiting reagent that affects the total or final mass of this product that we're trying to find. So let's first list our knowns. So we have the molar mass of magnesium hydroxide, which is 58.32 grams per mole. And we have the molar mass of HCl, so 36.46, and we have the mass of both of them right over here. So let's first calculate the moles for MgOH2. So we have the moles is equal to the mass over the molar mass. So our mass of MgOH2 is 12.0 grams over the molar mass, which is 58.32 grams per mole. So grams cancel out, and the answer is 12.0 divided by 58.32, 0.206 moles. So, and then now let us calculate the moles for HCl. So M over M again, 42.0 grams over the molar mass, which is 36.46 grams per mole. Grams cancel again, and the mole turns out to be 1.15 moles. So now we have the moles for each of these reactants, and now we have to figure out which one of these reactants is going to be the limiting reagent. So the mole ratio of magnesium hydroxide to HCl is 1/2. And say, let's individually use the moles for the magnesium hydroxide first, and say it's 0.206. And then let's figure out how many moles of HCl we need in order for this reaction to be perfect. So 0.206 times 2 divided by 1, cross multiply, and you have 0.412 moles. So we only need, for this reaction, we only need 0.412 moles of HCl. However, we have 1.15 moles, which is more than we need, which means that magnesium hydroxide is the limiting reagent because we have more than enough HCl we need in order to react with the MgOH2. Okay, so now let us erase this all, and we will treat our MgOH2 as the limiting reagent and compare it with our MgCl2. So the mole ratio, as we see here, between MgOH2 and MgCl2 is 1/1, correct? And we have 0.0206 moles of magnesium hydroxide over the unknown amount for MgCl2. So using the mole ratios, we can therefore conclude that 0.206 moles of MgCl2 are also made in this reaction because MgO2 is the limiting reagent. So now we have the moles of MgCl2. Let's find the mass. And the mass is moles over molar mass, as we know. So moles over molar mass, so 0.206 moles over the molar mass of MgCl2, which is, one second, let me look at my periodic table. So 95.21 grams per mole. So moles cancel out and we end up with 2.16 grams of MgCl2 produced from this reaction. And lastly, we have here pharmaceutical production. So this is one of the applications mentioned earlier of percent yield, theoretical yield, and limiting reagents together. So the world of pharmaceutical production is an expensive one. So many drugs have several steps in their synthesis and use costly chemicals. And a great deal of research takes place here to develop better ways to make drugs faster and more efficiently. And studying how much of a compound is produced in any given reaction is an important part of cost control economically. So an example of this could be SSRIs, and those are selective serotonin inhibitors that are used to treat depression, right? And scientists, when synthesizing these medications, have to consider the limiting reagents and the percent yield of the chemical reactions to ensure optimum effectiveness and minimal wasting of products, right? And yeah, that is the premise of pharmaceutical production when it comes to limiting reagents and percent yield.